What are the best vegan technologies for planetary regeneration? Vegan technologies for planetary regeneration are those that replace animal-based systems with plant-based, microbial, or synthetic alternatives while actively restoring ecosystems, reducing emissions, and regenerating biodiversity. They eliminate the destructive impacts of industrial animal agriculture, deforestation, methane, water use, biodiversity loss, and instead contribute to a regenerative and circular bioeconomy. Here's a comprehensive breakdown of the best ones. Plant-based food production technologies. Vertical farms and aeroponics use minimal land and water to produce fruits, vegetables, and legumes in cities, eliminating pressure to clear land for grazing or feed crops. Precision irrigation and AI farming reduces water waste and improves yields without harming ecosystems. Agroforestry and food forests. Plant-based food grown alongside trees mimics rainforest ecosystems, regenerating soil and biodiversity. Cellular agriculture and fermentation. Precision fermentation uses microbes, yeast, fungi, bacteria, to produce milk proteins, egg whites, collagen, and honey without animals. Companies already produce casein, whey, and albumin in bioreactors. Microbial protein, single-cell protein, algae, fungi, highly efficient protein sources grown with almost no land use, restoring land for rewilding. Mycelium and plant-based materials. Mycelium leather and biocomposites replace animal leather and plastics with biodegradable, fungal-based alternatives. Plant-based packaging replaces single-use plastics and styrofoam with fibers, starches, and seaweed-based films. Hemp and bamboo materials, renewable raw materials for textiles, paper, and construction, reducing logging and industrial livestock leather. Soil and ecosystem regeneration technologies. Vegan biofertilizers, produced from compost, algae, and microbes instead of animal manure or blood-bone meal, restoring soil microbiomes without factory farming byproducts. Carbon sequestering crops, perennial grains, legumes, and cover crops regenerate degraded soils while producing vegan food. Rewilding drones plant trees, restore grasslands, and regenerate ecosystems freed from livestock grazing. Vegan energy and fuel alternatives. Algae biofuels replace fossil fuels without competing with food crops or harming animals. Plant and waste-based biogas captures methane from food waste instead of manure lagoons from animal farms. Solar and plant-inspired photosynthetic materials, technologies that mimic natural photosynthesis to turn CO2 and sunlight into fuels without relying on animal fats. Vegan cities and circular industry. Plant-based construction materials, hempcrete, bamboo composites, and mycelium bricks replace concrete and steel, lowering emissions. Algae architecture, buildings that grow algae for CO2 capture and bio-based products. Closed-loop vegan supply chains, industry designed without animal exploitation, turning plant and microbial waste into energy, fertilizers, and new products. Biotechnologies for climate and habitat healing. Microalgae and cyanobacteria bioreactors capture CO2 while producing protein, omega-3s, and bio-based chemicals. Synthetic photosynthesis systems, artificial leaves that produce vegan fuels, food ingredients, or fertilizers from sunlight and air. CRISPR edited crops, climate-resilient plant varieties that reduce pressure on ecosystems and ensure food security without livestock. Vegan circular economy platforms. Food waste valorization, converting plant waste into vegan fertilizers, bioplastics, textiles, and fuels. Fungi and algae-based recycling, biological systems that break down plastics and industrial waste into usable materials. Vegan carbon capture products, using captured CO2 to produce plant-based polymers, textiles, or food ingredients instead of animal-based goods. Planetary impact. Rewilding land currently used for animal agriculture could restore 60 to 70% of biodiversity loss and absorb gigatons of CO2. Vegan technologies enable this transition while replacing every animal-based industry with sustainable, regenerative alternatives. Comprehensive explanation of vegan technologies for planetary regeneration. Vegan technologies are technological and biological solutions that replace or avoid animal-based systems and materials while actively restoring ecosystems, reducing greenhouse gas emissions, and improving biodiversity and human well-being. When used at scale, these technologies reduce the land, water, and nutrient pressures caused by animal agriculture and open opportunities to restore ecosystems, sequester carbon, and build circular supply chains that close resource loops. Below I explain the major categories, how they work, why they help planetary regeneration, what trade-offs and obstacles exist, and concrete pathways for implementation. What counts as a vegan technology? A vegan technology is any tool, process, material, or system that provides the functions society currently gets from animals, food, materials, labor, biochemical inputs, without relying on animal life. This includes plant-based production systems, microbial and fermentation processes, engineered cell-based products that do not require raising animals, biomaterials derived from fungi and plants, and systems-level changes, such as circular bioeconomies and policy instruments, that enable those technologies to scale. Food system technologies and how they regenerate the planet. Plant-forward production, microbial protein, precision fermentation, and cell-cultured products replace much of the demand for meat, dairy, and eggs. Plant-based crops require far less land per calorie or protein than livestock, and shifting land away from feed and grazing reduces deforestation and habitat conversion. Microbial single-cell protein, grown from bacteria, yeast, fungi, or algae in bioreactors, can supply protein with extremely low land footprint and can be powered by low-carbon energy. Precision fermentation programs microbes to produce animal equivalent proteins such as casein or egg albumin so that foods with the same functional and nutritional properties can be made without animals. Together, these technologies free large areas of land that can be used for rewilding, afforestation, or regenerative agriculture that restores soils and biodiversity. Regenerative crop systems and landscape design. Regenerative plant agriculture, comprising agroforestry, perennial polycultures, cover cropping, and reduced tillage, rebuilds soil organic matter, enhances water retention, and supports diverse species. Agroforestry systems integrate trees with food crops and can supply fruit, nuts, timber, and habitat while sequestering carbon in biomass and soil. Perennial grains and multi-strata food forests reduce yearly soil disturbance and create stable carbon sinks compared with annual monocultures or livestock pastures. Implementing these designs at landscape scale simultaneously produces food and restores ecosystem function. Microbial, fungal, and plant-based materials. Mycelium, fungal root networks, can be engineered into strong, lightweight, biodegradable materials that replace leather, plastics, packaging, and some building materials. Plant fiber composites, made from hemp, bamboo, kenaf, or agricultural residues, provide renewable alternatives to timber and fossil-derived materials. Microbial fermentation produces biopolymers and proteins that serve as feedstocks for textiles, adhesives, and composites. Using these materials reduces logging, mining, and the greenhouse gas intensity of material production, while creating products that are biodegradable or easier to recycle. Energy, fuels, and synthetic photosynthesis. Algal bioreactors and engineered microbes can produce biofuels, bioplastics, and lipid-rich oils without diverting cropland from food production. Synthetic or biomimetic photosynthesis systems aim to convert sunlight and CO2 directly into chemical fuels or feedstocks, offering pathways to store renewable energy in stable molecular forms. When coupled with low-carbon electricity, these technologies can provide energy carriers without the land use footprint and methane emissions associated with animal agriculture and fossil fuels. Waste valorization and circular bioeconomies. Vegan technologies emphasize converting plant and food system waste into value by upcycling them into fertilizer, feedstock for microbial fermentation, biogas, or soil amendments. Anaerobic digestion and composting systems turn crop residues and processing waste into energy and soil inputs, rather than letting those resources decompose inefficiently or be burned. Biorefineries can fractionate plant biomass into multiple products, fuels, fibers, chemicals, and nutrients, so that almost every output is used and waste is minimized. Soil, carbon, and ecosystem restoration tools. Biochar, layered composts, and microbe-based biofertilizers increase soil carbon and nutrient holding capacity. Assisted restoration using seedball drones or precision reforestation tools accelerates landscape recovery on land freed from livestock grazing. Native species reintroduction and corridor design restore habitat connectivity and enable wildlife to recover. These approaches not only sequester carbon but also rebuild functional ecosystems that support pollinators, predators, and plant diversity. Urban and infrastructure innovations. Vertical farming, controlled environment agriculture, and rooftop production can supply fresh vegetables and herbs close to consumers while using less water and land. Green building materials derived from plants and fungi reduce embodied carbon in construction. Urban nutrient recycling, collecting food waste and converting it to soil amendments, keeps carbon and nutrients in the urban-rural loop rather than losing them to landfills. Biotechnology, plant breeding, and resilience. Modern breeding and microbial engineering produce crop varieties and soil microbiomes that tolerate drought, resist pests, and use nutrients more efficiently. These advances reduce the need for intensive chemical inputs and expand the range of climates where plant-based systems can reliably feed people. When coupled with agroecological design, resilient crops support long-term regeneration rather than extractive production. Why these technologies support planetary regeneration? Vegan technologies reduce the major environmental pressures caused by livestock, including land conversion for grazing and feed, methane emissions from enteric fermentation, nutrient runoff from concentrated animal operations, and biodiversity loss from habitat destruction. By lowering the land footprint of food and materials, these technologies make it feasible to rewild a forest and restore native ecosystems at scale. Moreover, circular designs retain nutrients on the landscape, improve soil health, and reduce reliance on finite mineral resources. Co-benefits for public health, economy, and communities. Widespread adoption of vegan technologies can lower zoonotic disease risks by reducing animal crowding and intensive confinement. Plant and microbe-based food systems can be more nutrient-dense and less contaminated with antibiotic residues. New industries, mycelium manufacturing, precision fermentation, algal biorefineries, create jobs and regional value chains that are less volatile than commodity animal agriculture, particularly if policy supports localized processing and worker transition programs. Trade-offs, limits, and risks to manage scaling vegan technologies requires managing a set of trade-offs. Some industrial fermentation and bioreactor systems use considerable energy, so they must be powered by low-carbon electricity to be climate beneficial. Large-scale monoculture of replacement crops can reproduce the same ecological harms as past agriculture, so regenerative cropping practices are essential. Social, cultural, and economic barriers, including dietary preferences, incumbent industry resistance, and regulatory lag, can slow adoption. Careful life cycle assessment and ecosystem-based design are needed to avoid unintended consequences. Policy, finance, and governance pathways for scaling public policy can accelerate these technologies through research funding, procurement, for example, plant-based protein in public institutions, transitional subsidies for farmers shifting land out of animal agriculture, and reforming agricultural subsidies that currently favor livestock feed production. Carbon markets and payment for ecosystem services schemes can reward landowners for converting pastures to forests or restoring wetlands. Standards and transparent labeling for microbial, cell-based, and mycelium products help build consumer trust and regulatory clarity. Implementation roadmap, practical steps, in the short term, 1 to 5 years, expanding plant-based supply chains, scaling fermentation pilots, improving composting and waste collection, and funding farmer transition programs are high-impact priorities. In the medium term, 5 to 15 years, industrializing microbial protein, mainstreaming agroforestry and perennial crops, and building regional biorefineries will scale benefits. In the long term, 15+ years, integrating synthetic photosynthesis, widespread rewilding of freed lands, and systemic circular bioeconomies can transform landscapes and lock in long-term carbon sequestration. Monitoring, metrics, and success indicators. Success should be tracked with clear ecological and social metrics. Ecological metrics include net greenhouse gas emissions, including methane and nitrous oxide, soil organic carbon stocks, native species richness and abundance, water quality indices, and land area converted back to native habitat. Social and economic metrics include farmer incomes during transitions, job counts in new sectors, food affordability and accessibility, and public health indicators related to diet and zoonotic risk. Practical next actions and research priorities. Practical next steps include increasing funding for field trials of microbial foods and mycelium materials, piloting large-scale rewilding on land voluntarily retired from livestock production, investing in decentralized processing infrastructure so rural communities capture value, and creating education programs to retrain workers from intensive animal farming to regenerative plant systems and bioeconomy roles. Research priorities include life cycle assessments under realistic energy scenarios, long-duration field trials of perennial and agroforestry systems, and social science studies on dietary transition pathways. Vegan technologies form an integrated toolkit for planetary regeneration by replacing the most land and resource-intensive uses of animals with lower footprint plant and microbial systems. By restoring soils and ecosystems on the land that is freed, and by closing nutrient and carbon cycles so the biosphere can recover. The technologies are diverse, ranging from microbial fermentation and mycelium materials to agroecology, algal biofuels, and urban vertical farming, and each must be implemented with ecological design principles, supportive policy, and attention to social equity. If you would like, I can now convert this explanation into a sector-by-sector blueprint with timelines, key actors, and measurable targets tailored to a particular region or scale, city, national, or global. What are the best vegan technologies to increase sustainability and environmental conditions of the world in every region? Best vegan technologies to increase sustainability and environmental conditions in every region. Here is the most effective plant and microbe-based, vegan, technologies for improving sustainability and environmental conditions. Organized by broad region type of environment: tropical, temperate, arid, cold polar, island coastal, and dense urban. For each region I give the technologies that work best there, why they help, important trade-offs, and practical implementation steps you can pursue at community, regional, or national scale. All explanations are in complete sentences. Tropical regions, rainforests, humid lowlands. Tropical regions benefit most from technologies that protect remaining forest, restore degraded lands, and provide high-yield plant foods without expanding agricultural frontier. Agroforestry and multi-strata food forests. These systems grow trees, shrubs, and annuals together to produce food, timber, and non-timber products while restoring soil, increasing biomass carbon, and recreating wildlife habitat. Perennial crops and mixed perennial polycultures. Perennials reduce soil disturbance and build long-term soil carbon compared with annual monocultures or pasture. Community-scale precision fermentation and microbial protein hubs. Local fermentation facilities can produce protein and food ingredients from sugar or on-site feedstocks, lowering pressure to clear forest for pasture or feed crops. Mangrove and riparian restoration using seedball drones and community nurseries. Restored coastal ecosystems buffer storms, sequester carbon, and support fisheries that reduce reliance on extractive practices. Mycelium-based materials and plant fiber industries. Local production of fungal leather, packaging, and construction panels replaces timber extraction and animal leather. Soil building, biochar and composting with plant residues. Biochar stabilizes carbon in soil and improves water retention, which is crucial in degraded tropics. Implementation steps: prioritize land protection policies and payments for ecosystem services, support farmer training in agroforestry, invest in decentralized fermentation and mycelium processing, and fund restoration jobs for local communities. Trade-offs: agroforestry and perennial systems require technical support and time to become productive. Precision fermentation needs reliable electricity and feedstock logistics. Temperate regions, mixed farming, broadleaf forests, grasslands. Temperate areas can scale high-productivity plant systems, circular bioeconomies, and technologies that combine seasonal production with long-term soil regeneration. Regenerative annual cropping paired with perennial hedgerows and silvopasture conversion. Converting marginal livestock pastures into perennial biomass or food forests improves carbon storage and habitat. Large-scale precision fermentation in single-cell protein facilities. Temperate industrial infrastructure is often well-suited to centralizing microbial protein production to supply cities and export markets. Advanced organic amendments and biofertilizers. Locally produced microbial inoculants and plant-based compost replace animal manure while restoring soil microbiomes. Bio-based building materials, hempcrete, mycelium panels, straw board. These replace high-carbon construction inputs and create regional value chains. Constructed wetlands and enhanced wastewater reuse systems. These recover nutrients, clean water, and supply irrigation for urban agriculture. Cover cropping, reduce tillage, and precision nutrient management. These practices reduce erosion and nitrous oxide emissions while increasing yields. Implementation steps: use subsidy reform to favor regenerative cropping, develop regional biorefineries that convert straw and residues into materials and nutrients, and build municipal fermentation centers that serve institutional buyers. Trade-offs: industrial fermentation must be coupled to low-carbon electricity to be climate beneficial. Shifting subsidies and retraining labor requires political will. Arid and semi-arid regions, deserts, drylands. Dry regions need technologies that maximize water efficiency, restore degraded soils, and produce food without large water footprints. Desert-appropriate perennial crops in agroforestry, date palms, moringa, jojoba, lucerne. Perennials reduce evaporation losses and stabilize soils. Aeroponics and closed-loop hydroponics with water recapture. Controlled environment systems can produce high yields per liter of water when integrated with brackish or recycled water sources, fog and dew harvesting, managed aquifer recharge, and rainwater capture. Passive water harvesting supports plantings and recharges local water tables. Salt-tolerant halophyte agriculture and seaweed farming. For coastal drylands, halophytes can produce oils, fibers, and food on saline soils and brackish water. Biochar, mycorrhizal inoculation, and soil conditioners. These approaches improve soil water retention and fertility in marginal lands. Solar-powered desalination and algal bioreactors for protein and bioproducts. Coupling solar with low-energy desalination can provide water and feedstocks for microbial production. Implementation steps: prioritize locally adapted perennial species, invest in low-energy water technologies and training, and create incentives for halophyte and seaweed value chains. Trade-offs: desalination and closed systems can be energy-intensive unless renewable energy is abundant. High-tech systems require maintenance capacity. Cold and polar regions, boreal forests, tundra, cold regions need strategies that avoid permafrost disturbance, restore degraded boreal zones, and supply local food without importing high-carbon goods. Controlled environment agriculture and vertical farms optimized for low-energy heating. Using passive solar design, heat recovery, and efficient LED lighting supports local vegetable production. Perennial forage crops and rewilding of overgrazed areas. Restoring native vegetation reduces soil erosion and preserves permafrost insulation. Algal cultivation and insulated bioreactors. Algae can produce high-value oils and proteins using relatively compact facilities suited for remote regions. Biomass-based materials from managed boreal residues, small-scale mycelium and fiber processing. Local processing reduces transport emissions and creates building materials. Passive design for housing in microgrids with wind and solar. These technologies reduce fossil fuel heating demand while supporting local processing facilities. Implementation steps: support microgrid deployment, fund greenhouse projects with waste heat integration, and promote restoration programs that avoid disturbing sensitive permafrost. Trade-offs: infrastructure costs are high and ecosystems are fragile. Interventions must prioritize minimal ground disturbance. Island and coastal regions. Islands and coasts need resilient food systems, blue carbon restoration, and materials that reduce import dependence. Seaweed and shellfish-free aquaculture, vegan marine crops. Seaweed farms sequester carbon, reduce ocean acidification locally, and provide biomass for food, feed, and materials. Mangrove restoration and seagrass meadows. These blue carbon ecosystems protect coasts, support fisheries, and sequester carbon long-term. Rainwater harvesting, decentralized desalination with renewables, and constructed wetlands. These systems secure fresh water without relying on costly imports. Local plant-based food hubs and fermentation units. Small-scale fermentation can produce protein and ingredients from local carbohydrates and waste. Biodegradable seaweed-based packaging and local biomaterial production. These reduce plastic pollution and import burden. Implementation steps: couple seaweed farming with mangrove restoration projects, enable micro-grants for local bioprocessing, and use zoning to protect coastal ecosystems while allowing sustainable seaweed operations. Trade-offs: seaweed markets need stable value chains. Coastal restoration must be planned with community input to avoid displacement. Dense urban regions, cities and metropolitan areas. Cities are the centers of consumption and therefore crucial places to implement vegan technologies that close loops and lower footprints. Vertical farming, rooftop gardens, and distributed controlled environment agriculture. These reduce food miles and supply fresh produce year-round. City-scale anaerobic digestion of plant food waste and urban composting. These systems turn waste into energy and soil amendments for urban and peri-urban farms. Precision fermentation facilities sited near demand. Localized fermentation shortens supply chains for ingredients like milk proteins and egg alternatives. Green infrastructure, urban tree canopy expansion, permeable pavements, and rain gardens. These features cool cities, manage stormwater, and increase biodiversity. Circular material hubs using mycelium processing and textile recycling. Urban centers can become nodes for upcycling and producing vegan biomaterials. Policy levers like institutional procurement, zoning for urban farms, and building codes that favor low-carbon materials. Municipal leadership accelerates market uptake. Implementation steps: adopt municipal targets for food waste diversion, underwrite fermentation and mycelium pilot projects, and use public procurement to create demand for plant-based products. Trade-offs: urban land is scarce, Vertical farms require capital and optimized logistics to be cost competitive. Cross-cutting technologies that benefit every region. These technologies are useful across climates and geographies and form the backbone of a global vegan regenerative transition. Precision fermentation and single-cell protein. These technologies produce high-quality protein, fats, and specialty ingredients with low land footprint and can be sited near demand or feedstock sources. Mycelium engineering and plant fiber biocomposites. These materials replace leather, plastics, and many timber uses while offering biodegradability and lower embodied carbon. Soil restoration tools, biochar, microbial inoculants, and compost systems. Healthy soils sequester carbon, increase yields, and retain water. Algal biorefineries and seaweed valorization. Algae produce food, feed, fuels, and chemicals without competing for arable land. Decentralized renewable energy, solar, wind, microgrids. These power fermentation, desalination, and greenhouse systems while minimizing life cycle emissions. Waste-to-value systems, anaerobic digestion, biorefineries, and circular nutrient loops. These keep carbon and nutrients on the landscape and reduce pollution. Digital tools, precision agriculture, remote sensing, and supply chain traceability. Data reduces inputs, improves yields, and increases transparency for vegan products. Policy, finance, and social measures required everywhere. Technology alone is insufficient. Enabling policies and finance are required in every region. Redirect agricultural subsidies toward regenerative plant systems and farmer transition payments. Financial incentives accelerate land conversion away from livestock. Invest in workforce retraining and rural processing infrastructure. These steps preserve livelihoods while changing the production base. Public procurement of vegan foods and materials. Governments, schools, and hospitals create early markets and scale. Payments for ecosystem services and carbon removal credits tied to verified ecological outcomes. These fund rewilding, afforestation, and restoration. Standards and testing for novel foods and materials. Clear regulation builds consumer trust and ensures safety and environmental benefits. Metrics to monitor success. Regions should track a concise set of indicators to measure environmental improvement. Land area returned to native habitat or converted to low-impact perennial systems. Net greenhouse gas emissions, including CO2, methane, and nitrous oxide, from the food and material sectors. Soil organic carbon and topsoil depth across representative landscapes. Freshwater use per unit of food or material produced. Native species richness and key indicator populations. Volume of plant and microbe-based products produced locally and food waste diversion rates. Important trade-offs and risks to manage. All regions must manage similar risks to avoid unintended harm. Energy intensity of advanced food systems. Fermentation and controlled environment. Agriculture must run on low-carbon electricity to deliver climate benefits. Monoculture replacement risks. Replacing animal agriculture with large monocultures reproduces biodiversity loss. Regenerative design and polyculture must be the norm. Social and cultural acceptance. Policy should be equitable and co-designed with local communities to avoid displacement. Supply chain bottlenecks. New industries need logistics, standards, and training to scale without damaging ecosystems. Concrete immediate actions. What communities, governments, and businesses can do now. Scale municipal and institutional procurement of plant-based foods to create reliable demand for producers. Fund pilot fermentation, mycelium, and algal processing centers in agricultural regions to build local value chains. Offer farmer transition programs that pay for converting marginal pasture to agroforestry, perennial crops, or rewilding. Invest in urban composting and anaerobic digestion to close nutrient loops and supply soil amendments. Deploy renewable energy microgrids to power low-carbon food production and water systems. Protect high-value natural habitats legally and implement community-led restoration projects that provide jobs and ecosystem services. Different climates and geographies demand different mixes of vegan technologies, but the common thread is clear: plant and microbe-based production, regenerative landscape design, circular waste-to-value systems, renewable energy integration, and supportive policy together enable global improvements in sustainability and environmental conditions. When these technologies are implemented with ecological design, local adaptation, and social equity, they reduce emissions, restore soils and biodiversity, secure water and food for communities, and create resilient local economies. Vegan technologies replace animal-based systems with plant, fungal, or microbial systems and associated engineering, while deliberately prioritizing ecological restoration, circular resource flows, and social equity. Implemented with ecological design and appropriate policy support, these technologies reduce land conversion, greenhouse gas emissions, pollution, and biodiversity loss, while creating new livelihoods and regional value chains. Tropical regions, rainforests, humid lowlands, agroforestry, and multi-strata food forests integrate trees, shrubs, vines, and annual crops into a single production system so that food, fuel, and fiber are produced in layers that emulate natural forests. These systems sequester carbon above and below ground, prevent erosion, conserve moisture, and provide habitat for wildlife while reducing pressure to clear native forest for pasture or monoculture. The main trade-offs are the long establishment time and the need for local technical support and market development for diverse products. Practical implementation begins with community-led demonstration plots, extension services for farmers, and market channels that value diverse, forest-friendly products. Perennial crops and mixed perennial polycultures replace annual monocultures and pasture with long-lived species that stabilize soils, build deep carbon stocks, and require less annual tillage. Perennials reduce nutrient runoff and often require fewer synthetic inputs than annual systems when managed as diverse polycultures. The principal challenge is matching species and management practices to local soils and markets so that farmers receive income during the establishment phase. Rolling incentives, transitional payments, and crop insurance adapted to perennial systems help overcome adoption barriers. Community-scale precision fermentation and microbial protein hubs use small to medium bioreactors to produce proteins, lipids, and other ingredients locally from sugars, residues, or sustainably produced feedstocks. These facilities lower demand for livestock-derived protein and reduce the need to expand cropland into forests. The risks include energy demands and the need for regulatory clarity and food safety systems. Setting up pilot facilities with renewable electricity, local feedstock linkages, and cooperative ownership models can provide proof of concept and build local value. Mangrove and riparian restoration using seedball drones, community nurseries, and traditional planting techniques re-establish blue carbon habitats that protect coasts, store carbon, and provide nursery grounds for fish. Restoring these ecosystems also stabilizes shorelines against storms and supports local fisheries without intensifying destructive practices. The trade-offs include ensuring that restoration is guided by local ecological knowledge and that it does not displace other community uses of the land. Scaling such restoration requires secure tenure, payment for ecosystem services mechanisms, and investment in community workforce training. Mycelium-based materials and plant fiber industries convert local agricultural residues, tropical fibers, and fungal mycelium into leather substitutes, packaging, and building panels so that forest-dependent communities can earn income without cutting trees or raising animals. These biomaterials reduce embodied carbon and are often biodegradable, which lowers long-term waste. Technical capacity building, quality control, and market development are necessary to make these value chains commercially viable. Creating regional processing hubs and linking producers to designers and buyers accelerates commercialization. Soil building with biochar and composting uses plant residues and community waste streams to create stable soil amendments that increase soil organic carbon and water retention. These practices improve crop resilience during droughts and reduce the need for synthetic fertilizers that can harm waterways. The main constraints are initial labor, equipment for making stable biochar at scale, and ensuring feedstock sustainability. Local cooperatives, small-scale pyrolysis units, and municipal compost programs provide practical entry points. Temperate regions, mixed farming, broadleaf forests, grasslands, regenerative annual cropping paired with perennial hedgerows and silvopasture conversion combines improved annual crop practices with permanent perennial elements so that fields produce crops while supporting biodiversity and carbon storage. Such integrated systems reduce erosion, lower fertilizer losses, and provide habitat corridors across working landscapes. Trade-offs include redesigning farm economics and supply chains to value ecosystem services. Policymakers can accelerate adoption by providing payments for environmental outcomes and technical assistance. Large-scale precision fermentation and single-cell protein facilities in temperate regions leverage existing industrial infrastructure and stable energy grids to produce protein, dairy analogs, and specialty ingredients at scale. This industrial capacity reduces reliance on livestock and can supply both local and export markets. The environmental benefit depends on low-carbon energy inputs and efficient feedstock logistics. Securing renewable power contracts, optimizing life cycle energy use, and siting facilities near waste or biomass feedstocks are practical steps. Advanced organic amendments and biofertilizers produced from plant residues and beneficial microbes restore soil microbiomes and nutrient cycling so that cropped soils regain productivity without relying on manure from industrial animal systems. These inputs improve plant health and resilience while reducing nitrogen and phosphorus pollution. The risks include variable product quality and the need for regional testing to match inoculants to soils. Supporting regional research stations and farmer field trials helps validate and scale effective formulations. Bio-based building materials such as hempcrete, strawboard, and mycelium panels replace steel and concrete in many applications so that construction embodies less carbon and uses renewable feedstocks. These materials can be produced from agricultural residues and regional crops, creating local jobs. Structural codes and performance certification are necessary to ensure safety and market acceptance. Pilot public buildings and incentives for low-carbon materials accelerate mainstream adoption. Constructed wetlands and enhanced wastewater reuse systems treat urban and agricultural effluents while recovering nutrients and providing habitats so that water quality improves and reclaimed water supports irrigation. These systems lower nutrient loads entering rivers and replenish water for peri-urban farms. Space requirements and initial capital costs are trade-offs that can be addressed by integrating wetlands into parks and multifunctional landscapes. Municipal investment and public-private partnerships can finance these systems. Cover cropping, reduce tillage, and precision nutrient management work together to lock carbon into soils, reduce erosion, and prevent nitrous oxide emissions so that temperate farms become more climate resilient. These approaches require farmer training and sometimes new equipment, but they pay back through lower input costs and improve yields over time. Extension programs and cost-share schemes reduce the upfront barriers to adoption. Arid and semi-arid regions, deserts, drylands, desert-appropriate perennial crops and agroforestry use drought-tolerant trees and shrubs that stabilize soils, provide shade, and produce diverse food and fiber so that marginal lands become productive without large water inputs. These plants improve microclimates and reduce dust and erosion. Careful species selection and water harvesting designs are critical to avoid maladapted plantings that fail or consume scarce groundwater. Community nursery programs and demonstration sites support successful establishment. Aeroponics and closed-loop hydroponics with water recapture produce vegetables with minimal water use by recycling and reconditioning nutrient solutions so that high-value produce can be grown even in extremely dry areas. These systems require technical management and reliable energy, but they reduce pressure on regional freshwater resources compared with irrigated field crops. Hybrid systems that use treated wastewater and renewable energy reduce operational risk. Training local technicians and deploying modular units helps communities adopt these systems. Fog and dew harvesting, managed aquifer recharge, and rainwater capture are low-tech and high-impact approaches that collect atmospheric moisture and episodic rain so that small plantings can survive and groundwater is replenished. These passive systems are inexpensive and community manageable, but they must be integrated into broader water management to prevent overuse. Local governance structures and maintenance plans are essential for long-term success. Salt-tolerant halophyte agriculture and seaweed farming provide food, oils, and biomass on saline soils or brackish water so that agriculture expands without competing for fresh water or fertile land. These systems create new coastal economies and can remediate saline soils over time. Market development and processing infrastructure are required to turn biomass into valuable products. Public investment in pilot value chains and demonstration farms helps create markets. Biochar, mycorrhizal inoculation, and soil conditioners increase moisture retention and nutrient availability in degraded arid soils so that plantings establish more successfully and require less irrigation. These amendments must be produced sustainably and applied in amounts appropriate to avoid unintended soil chemistry changes. Small-scale production units and farmer cooperatives help scale these inputs affordably. Solar-powered desalination and algal bioreactors combine renewable energy with low-energy desalination and algae cultivation so that water and high-protein biomass are produced for local use. These solutions are energy and capital intensive, so they are most viable where solar resource and financing are available. Carefully designed pilots with community ownership and maintenance plans demonstrate viability and reduce project risk. Cold and polar regions, boreal forests, tundra, controlled environment agriculture and vertical farms optimized for low-energy heating use passive solar design, heat recovery, and efficient lighting to produce fresh vegetables close to remote communities so that food security improves without high transport emissions. These systems reduce the need to import perishables and can integrate with local energy sources such as waste heat or microgrids. High capital costs and the need for skilled operators are challenges that can be mitigated by modular systems and training programs. Integrating greenhouses with district heating and local energy planning improves economics. Perennial forage crops and rewilding of overgrazed areas restore native vegetation that stabilizes soils, reduces erosion, and helps preserve permafrost by restoring insulating plant cover. Protecting these landscapes from further degradation helps avoid large carbon releases from soils. Restoration must avoid heavy machinery that can damage sensitive soils and should emphasize native species and low disturbance techniques. Funding mechanisms that reward landowners for conservation outcomes support longer-term stewardship. Algal cultivation in insulated bioreactors produces oils, proteins, and specialty biochemicals in compact facilities so that remote regions can develop high-value production without large land use. While energy inputs are a consideration, integrating algae production with local waste heat and renewable electricity improves efficiency. Technical support for maintaining cultures and ensuring product quality is necessary for market success. Partnerships with research institutes help develop strains and processing methods adapted to local conditions. Biomass-based materials from managed boreal residues, processed with mycelium and fiber technologies, provide local building materials and reduce the need to import timber or fossil-intensive materials. Processing must respect forest management standards so that residues are removed sustainably and biodiversity is preserved. Regional processing centers and community cooperatives help capture local value from these materials. Passive housing design and microgrids that combine wind and solar reduce fossil fuel heating demand while powering local food and material processing facilities. These integrated infrastructure investments lower operating costs and enhance resilience for remote communities. Public financing and community ownership models lower the capital hurdle and ensure that benefits remain local. Island and coastal regions seaweed farming and vegan marine cropping cultivate macroalgae that sequester carbon locally, provide biomass for food and materials, and improve coastal water quality by uptaking nutrients. Seaweed production creates coastal livelihoods while reducing dependence on imported goods. Market stability and logistics for drying and processing seaweed are practical challenges that can be overcome with cooperative processing hubs and value-added product development. Linking seaweed farming to coastal restoration projects increases ecological and social benefits. Mangrove restoration and seagrass meadow rehabilitation protect coasts from storms, sequester blue carbon, and support fisheries so that communities can rely on healthier marine ecosystems instead of destructive practices. Restoration must be guided by sound ecological planning and community consent to avoid unintended social impacts. Payment for ecosystem services and tourism-linked funding can generate revenue streams to sustain restoration. Rainwater harvesting, decentralized desalination with renewables, and constructed wetlands secure freshwater supplies and recycle wastewater so that island communities become more self-reliant. These systems reduce vulnerability to external supply disruptions but require maintenance and appropriate governance. Capacity building and small-scale modular technologies reduce the complexity of deployment. Local plant-based food hubs and fermentation units turn island-produced carbohydrates and agricultural residues into protein and specialty ingredients so that islands retain more value from their biomass and reduce imports. The main constraints are scale and consistent feedstock supply, which community planning and crop diversification can address. Small pilot projects and municipal procurement help create steady demand. Biodegradable seaweed-based packaging and local biomaterial production reduce plastic pollution and the import bill so that islands preserve coastal ecosystems and create new industries. Ensuring product standards and connecting producers to export markets increases economic viability. Dense urban regions, cities and metropolitan areas, vertical farming, rooftop gardens, and distributed controlled environment agriculture supply fresh produce close to consumers so that food miles decline and urban nutrition improves. These systems also provide green space, reduce urban heat islands, and can use captured rainwater and recycled nutrients. High capital and electricity needs are trade-offs that are best addressed with energy-efficient designs and integration of district energy or waste heat sources. Municipal incentives and public-private partnerships accelerate deployment. City-scale anaerobic digestion of plant food waste and municipal composting convert organic waste into energy and soil amendments so that nutrients are returned to peri-urban farms rather than lost to landfills. These systems close nutrient loops and reduce methane emissions from uncontrolled decomposition. Ensuring high diversion rates from households and businesses requires convenient collection systems and public education. Contracts with urban farms and landscapers create guaranteed outlets for compost and digestate. Precision fermentation facilities sited near demand produce specialty ingredients such as milk proteins and egg alternatives so that supply chains are shorter and logistics simpler. Local fermentation reduces transportation emissions and allows rapid adaptation to consumer preferences. Regulatory oversight and food safety systems must be in place to ensure consumer confidence. Pilot procurement by institutions and restaurants helps build the initial market. Green infrastructure such as tree canopy expansion, permeable pavements, and rain gardens cool cities, reduce stormwater runoff, and increase urban biodiversity so that cities become more livable and resilient. Implementing these measures requires cross-departmental planning and attention to equitable distribution across neighborhoods. Municipal green-blue networks combined with heat vulnerability mapping direct investments to the places of greatest need. Circular material hubs using mycelium processing and textile recycling transform urban waste streams into new materials so that cities become producers of biomaterials rather than net waste generators. These hubs require sorting infrastructure, collaboration with designers, and stable demand from local builders and manufacturers. Zoning and small-scale industrial policy can create space for these circular enterprises. Cross-cutting technologies that benefit every region. Precision fermentation and single-cell protein produce high-quality protein, fats, and specialty ingredients in controlled bioreactors so that nearly all culinary and industrial functions of animal products can be supplied without livestock. When powered with renewable energy and paired with local feedstock logistics, these technologies greatly reduce land and water footprints. The main risks are energy use and regulatory and social acceptance, which are addressed through life cycle optimization, clear safety frameworks, and transparent labeling. Mycelium engineering and plant fiber biocomposites create durable, biodegradable materials from fungi and plant residues so that leather, packaging, and some construction uses can be replaced with low-impact alternatives. These materials reduce embodied carbon and often biodegrade at end of life, closing material loops. Ensuring consistent material properties and scaling production requires investment in standardization and manufacturing processes. Soil restoration tools such as biochar, microbial inoculants, and compost systems rebuild soil organic matter and nutrient cycling so that landscapes store more carbon, retain water better, and support a wider range of plant species. The effectiveness of these tools depends on matching treatments to soil types and avoiding over-application. Regional demonstration programs and farmer-led trials identify best practices. Algal biorefineries and seaweed valorization convert sunlight, CO2, and nutrients into biomass for food, feed, fuels, and chemicals so that production does not compete for arable land and can provide coastal and inland value chains. These systems require reliable processing infrastructure and market development to realize their full economic potential. Strategic public investment in processing and product development accelerates commercialization. Decentralized renewable energy such as solar, wind, and microgrids provides the low-carbon power required to make fermentation, desalination, vertical farming, and other technologies climate positive. Integrated planning that couples energy systems with production facilities reduces transmission losses and increases resilience. Financing models like community ownership and green bonds make these systems equitable and financially viable. Waste-to-value systems, anaerobic digestion, composting, and biorefineries convert organic residues into energy, soil amendments, and feedstock so that waste becomes a resource rather than a pollution source. These systems require reliable feedstock streams and quality control to produce consistent outputs. Urban and regional waste collection reforms and contractual outlets for outputs support viability. Digital tools, remote sensing, precision agriculture, and supply chain traceability optimize inputs, reduce waste, and provide transparency so that environmental outcomes can be measured and improved. Data governance and access must be fair so that farmers and communities benefit from the information produced. Public-private partnerships to develop locally relevant tools ensure uptake. Policy, finance, and social measures required everywhere. Redirecting agricultural subsidies away from feed and livestock toward regenerative plant systems accelerates land use transitions and supports farmers during the early years of change. Workforce retraining programs and rural processing investments enable farm workers and communities to shift to new value chains without losing livelihoods. Public procurement of plant-based foods and biomaterials creates reliable demand that de-risks private investment. Payments for ecosystem services and verified carbon removal credits reward landowners for restoration outcomes, while clear standards and safety testing build consumer trust in novel foods and materials. Each technology described above improves sustainability when it is adapted to local ecology, culture, and economies, and when it is combined with enabling policy and social measures. If you would like, I can now produce a focused implementation plan for a specific region or scale, for example, a 5-year plan for a tropical province, a U.S. temperate state, or an island municipality that includes budgets, priority actions, and measurable targets. The best vegan technologies for planetary regeneration are those that restore ecosystems, eliminate dependence on animal exploitation, and create closed-loop, plant and microbe-based systems that regenerate soil, water, air, and biodiversity. These technologies combine food, materials, energy, and environmental restoration in ways that heal the planet rather than deplete it. Below is a comprehensive explanation in complete sentences. Plant-based food system shifting from animal-based agriculture to high-yield, low-impact plant agriculture regenerates ecosystems by freeing land for rewilding and afforestation. Staple crops such as legumes, grains, fruits, nuts, and vegetables can supply human nutrition with far less land, water, and emissions. Innovations like perennial grain breeding, climate-resilient pulses, and vertical farming allow for sustainable production in every region. Precision fermentation in cellular agriculture, vegan applications. Precision fermentation uses microbes like yeast, fungi, and bacteria to produce proteins, fats, and nutrients identical to those in animal products without raising animals. This technology reduces methane emissions, spares billions of animals, and prevents deforestation driven by livestock feed demand. It can also produce omega-3 fatty acids, dairy proteins, and egg alternatives at scale with minimal environmental impact. Algae and seaweed cultivation. Microalgae and macroalgae are powerful vegan technologies because they absorb CO2, clean water, and grow rapidly without arable land or fresh water. Algae can be used for food, fertilizers, pharmaceuticals, fuels, and bioplastics. Seaweed farms regenerate coastal ecosystems, protect shorelines, and provide carbon-negative biomass. Expanding algal biorefineries worldwide could significantly reduce pressure on terrestrial ecosystems. Mycelium technologies. Mycelium, the root network of fungi, can replace leather, plastics, packaging, insulation, and even construction materials. It grows quickly on agricultural residues, sequesters carbon in durable products, and biodegrades safely at the end of its life cycle. Mycelium technologies eliminate the need for animal-derived leather and petroleum-based plastics, reducing pollution and deforestation while creating circular economies. Plant-based bioplastics and materials. Biopolymers made from corn, sugarcane, cassava, or seaweed can replace fossil fuel plastics. Combined with compostable packaging, these reduce plastic pollution in oceans and soils. Similarly, hempcrete, bamboo composites, and straw-based construction panels can substitute concrete, steel, and timber, reducing emissions and deforestation while locking carbon into buildings. Regenerative vegan agriculture. Agroforestry, food forests, no-till cropping, permaculture, and biochar use plant-based systems to restore soil fertility, increase carbon sequestration, and support biodiversity. Unlike livestock agriculture, which depletes soils and emits greenhouse gases, regenerative vegan agriculture uses cover crops, composting, and natural nutrient cycling to improve soil health while producing food. Biochar, made from crop residues, enhances water retention and locks carbon into the soil for centuries. Water saving and desert greening. Vegan systems. Vegan technologies such as hydroponics, aeroponics, and drip irrigation can produce vegetables, fruits, and legumes with minimal water. Salt-tolerant crops and halophyte farming use brackish or seawater to grow food and biofuel crops in arid zones. Coupled with solar power desalination, these systems regenerate drylands without animal exploitation or overgrazing, reversing desertification. Circular waste-to-value systems. Plant and microbial technologies transform waste into resources. Anaerobic digestion of food scraps produces renewable energy and organic fertilizers. Composting restores soil health without animal manure. Microbes and engineered enzymes break down plastics, textile fibers, and industrial waste into reusable raw materials. These systems create circular economies where nothing is wasted. Blue carbon and coastal restoration. Mangrove, seagrass, and kelp restoration are vegan strategies that regenerate ecosystems and store vast amounts of carbon. These habitats protect shorelines, restore marine biodiversity, and improve fisheries without reliance on animal aquaculture. Drone seeding and ocean permaculture platforms accelerate large-scale regeneration of coastal ecosystems. Renewable energy for vegan systems. Solar, wind, and geothermal energy provide the power base for vegan technologies. Renewable energy supports fermentation tanks, vertical farms, desalination units, and biorefineries. Unlike fossil fuels, renewables eliminate emissions while enabling sustainable production of plant-based foods and materials worldwide. Digital and AI tools for vegan regeneration. AI, drones, and sensors enable precision farming that reduces water, fertilizer, and land use while maximizing yields. Satellite monitoring helps track deforestation, biodiversity recovery, and soil carbon levels. These technologies guide vegan agricultural systems to be more efficient and regenerative. Global land rewilding enabled by vegan technologies. By replacing livestock production with plant-based and microbial systems, vast tracts of land can return to forests, savannas, wetlands, and grasslands. This global rewilding accelerates biodiversity recovery, improves water cycles, and draws down atmospheric CO2. Vegan technologies free up over 75% of agricultural land currently occupied by animal agriculture, making planetary regeneration possible at unprecedented scale. The best vegan technologies for planetary regeneration are those that replace destructive animal agriculture with plant and microbe-based systems that restore ecosystems, sequester carbon, and eliminate pollution. Precision fermentation, algae farming, mycelium materials, regenerative agriculture, bioplastics, and renewable-powered food production together create a circular, regenerative economy. By implementing these technologies globally, humanity can restore biodiversity, reverse climate change, and create a sustainable civilization that thrives in harmony with nature. What are the best vegan technologies to turn cities and industries extremely sustainable and regenerative? The best vegan technologies to make cities and industries extremely sustainable and regenerative are those that eliminate reliance on animals, replace destructive resource flows with plant and microbe-based cycles, and actively restore ecosystems while meeting human needs. Below I explain the most important categories in complete sentences: vegan urban food systems, vertical farms, rooftop gardens, and hydroponics grow vegetables, legumes, fruits, and herbs directly in cities with minimal land and water use. Community-scale precision fermentation hubs produce vegan proteins, dairy alternatives, and fats without livestock, reducing food miles and greenhouse gases. Algal bioreactors on rooftops and facades capture CO2, produce oxygen, and supply nutritious biomass for food and bioproducts. These systems regenerate by cutting land pressure outside cities, closing nutrient loops, and improving urban air quality. Plant and mycelium-based materials for industry. Mycelium composites replace leather, plastics, and styrofoam in packaging, textiles, and furniture. Hempcrete, bamboo composites, and straw board replace concrete, steel, and timber in construction, lowering embodied carbon. Seaweed and plant-based bioplastics substitute fossil fuel plastics in consumer goods and packaging, reducing waste and ocean pollution. These materials are biodegradable, carbon sequestering, and require fewer inputs than animal-derived or fossil-based alternatives. Circular vegan waste-to-value systems. Citywide composting of plant waste produces rich soil amendments for urban farms and green infrastructure without animal manure. Anaerobic digestion of organic matter generates renewable biogas for heating and electricity, while producing digestite as fertilizer. Industrial biorefineries transform crop residues, textile waste, and food byproducts into chemicals, fuels, and biomaterials. Such systems ensure that waste becomes a resource, closing industrial loops while eliminating landfill pollution. Blue and green infrastructure. Urban forests, food forests, and green corridors provide shade, capture CO2, filter air, and boost biodiversity. Rain gardens, green roofs, and permeable pavements filter storm water, reduce flooding, and restore natural hydrology. Coastal cities can integrate seaweed farms and mangrove restoration to buffer storm surges, capture carbon, and enhance marine biodiversity. This infrastructure regenerates ecosystems while making cities climate resilient. Vegan energy and water technology. Solar power, desalination, and water recycling plants supply clean water without harming aquatic ecosystems. Biochar, plant-based filtration, and constructed wetlands clean wastewater while producing useful byproducts. Algae and plant-based bioenergy supply carbon-neutral fuels for local use when paired with renewable electricity. These technologies keep cities self-sufficient in water and energy while maintaining ecological balance. Digital and AI tools for vegan regeneration. AI-powered urban farming systems optimize hydroponics and vertical farming yields with minimal energy and nutrients. IoT waste tracking systems monitor resource flows and ensure every scrap of biomass is recycled into new products. AI-driven urban planning tools simulate green corridors, forest expansion, and rooftop farms for maximum ecosystem benefit. Digital tools make vegan cities efficient, adaptive, and regenerative. Policy and governance tools. Municipal procurement of vegan foods and biomaterials creates stable demand for regenerative industries. Zoning codes that favor green roofs, vertical farms, and bio-based construction accelerate adoption of vegan technologies. Carbon and nutrient credit systems tied to plant-based regeneration reward industries that restore ecosystems. Policy ensures vegan technologies scale across entire urban and industrial systems rather than remaining isolated projects. Global industrial shifts powered by vegan innovation. Plant-based textile industries, hemp, flax, bamboo, replace leather, wool, and silk with biodegradable fibers. Mycelium and algae-based packaging replace plastic in global supply chains. Precision fermentation for industrial inputs, enzymes, oils, proteins decarbonizes everything from food to cosmetics to detergents. Vegan biorefineries and industrial zones recycle all organic waste into fuels, polymers, and nutrients. These industries regenerate by turning waste into feedstocks and eliminating animal exploitation from supply chains. The best vegan technologies for regenerative cities and industries are those that close loops, regenerate ecosystems, and eliminate dependence on animal or fossil resources. Vertical farms, precision fermentation hubs, mycelium and algae bioproducts, circular waste-to-value systems, renewable-powered water and energy infrastructure, and digital optimization together make cities self-sufficient, biodiverse, and climate-positive. Industries powered by plant and microbial innovation can shift from extractive to regenerative, transforming urban centers into living ecosystems that heal the planet. Vegan technologies for regenerative cities and industries. Cities and industries are the engines of human civilization, but they are also the largest contributors to climate change, biodiversity loss, and pollution. Most urban systems today are linear. Resources are extracted, consumed, and discarded, leaving behind waste and degraded ecosystems. Industries, likewise, often depend on animal exploitation and fossil-based inputs, which accelerate environmental collapse. A transformative solution lies in adopting vegan technologies, plant and microbe-based systems that meet human needs while restoring the planet. These technologies enable a shift from extractive, polluting infrastructure toward regenerative, self-sustaining cities and industries that harmonize with natural ecosystems. Vegan urban food systems. One of the most powerful ways to regenerate cities is to redesign how they produce and consume food. Vegan food technologies eliminate the inefficiencies of animal agriculture while creating circular, resilient urban food networks. Vertical farms, rooftop gardens, and hydroponic greenhouses allow cities to grow fruits, vegetables, legumes, and herbs locally, with drastically reduced land and water requirements. Precision fermentation hubs can be integrated into urban areas to produce vegan proteins, dairy alternatives, and specialty fats without animals, lowering food miles and greenhouse gas emissions. In parallel, algal bioreactors can be installed on rooftops or building facades to capture CO2, release oxygen, and provide nutrient-rich biomass for food and industry. Together, these systems shrink the ecological footprint of urban diets while liberating farmland for rewilding and carbon sequestration. Plant and mycelium-based materials for industries that manufacture consumer goods, packaging, and building materials can be reimagined using vegan innovations. Mycelium composites are emerging as sustainable replacements for leather, plastics, and styrofoam. They are biodegradable, lightweight, and require little energy to produce, making them ideal for packaging, textiles, and furniture. Construction can shift to hempcrete, bamboo composites, and straw board, which substitute for concrete, steel, and timber while sequestering carbon in buildings. Bioplastics made from seaweed, cassava, and sugarcane offer compostable alternatives to petroleum plastics, drastically reducing ocean pollution. By scaling these plant and fungus-based industries, cities can meet material demands without depleting ecosystems or depending on animal-derived resources. Circular vegan waste-to-value systems. A regenerative city does not treat waste as a problem but as a resource. Vegan waste-to-value technologies close loops in urban systems. Citywide composting transforms plant food waste into nutrient-rich soil amendments that feed urban farms and green infrastructure. Anaerobic digestion turns organic matter into biogas for heating and electricity, with digestate used as fertilizer. Industrial biorefineries can upcycle textile scraps, crop residues, and food processing byproducts into biofuels, biomaterials, and valuable chemicals. These circular processes reduce pollution, divert waste from landfills, and replace fossil inputs with renewable alternatives, ensuring that resources continually cycle through the urban economy. Blue and green infrastructure cities can regenerate ecosystems by embedding blue and green infrastructure into their design. Urban forests, food forests, and green corridors increase carbon sequestration, cool urban heat islands, and restore habitats for pollinators and birds. Rain gardens, green roofs, and permeable pavements capture and filter storm water, reducing flooding and replenishing aquifers. In coastal areas, vegan blue technologies such as seaweed farms and mangrove restoration strengthen natural defenses against storm surges, capture carbon, and restore marine biodiversity. These living systems transform cities into ecological landscapes that regenerate biodiversity while making urban environments more livable and resilient. Vegan energy and water technologies. Regenerative cities must meet their energy and water needs without damaging ecosystems. Vegan technologies offer solutions by integrating renewable power with circular water management. Solar-powered desalination and advanced recycling systems can secure fresh water supplies for urban populations. Constructed wetlands and plant-based biofiltration clean wastewater naturally while creating wildlife habitat. Biochar and plant-based filtration systems restore soil and groundwater quality. In addition, algae and plant-based bioenergy can complement solar and wind to provide carbon-neutral energy sources for local use. When combined, these technologies ensure that cities are self-sufficient in energy and water without relying on animal agriculture or fossil fuels. Digital and AI tools for vegan regeneration. The complexity of regenerative cities requires advanced digital systems to optimize flows of food, energy, water, and materials. AI-powered farming systems manage hydroponics and vertical farms with precision, maximizing yields while minimizing inputs. IoT-based waste tracking ensures that every biomass stream is diverted to composting, digestion, or biorefining. AI-driven planning tools simulate the ecological impact of new green corridors, rooftop farms, or algae installations, allowing urban designers to maximize regeneration benefits. These digital systems transform vegan technologies into efficient, scalable solutions capable of serving millions of people sustainably. Policy and governance for vegan innovation technology must be supported by governance and policy to scale across cities and industries. Municipal procurement of vegan foods, biomaterials, and bioplastics creates reliable demand and accelerates innovation. Zoning codes can require green roofs, vertical farms, and bio-based construction materials for new developments. Carbon and nutrient credit systems tied to plant-based regeneration reward industries that actively restore ecosystems. By aligning policy frameworks with vegan technologies, governments can ensure that urban and industrial transitions happen rapidly, equitably, and at scale. Global industrial transformation. Industries beyond city boundaries also benefit from vegan innovation. Plant-based textile industries replace wool, leather, and silk with hemp, flax, bamboo, and fungal fibers. Mycelium and algae-based packaging substitutes for single-use plastics in global supply chains. Precision fermentation produces not only food ingredients but also industrial enzymes, oils, and specialty chemicals with lower carbon footprints. Vegan biorefineries can recycle agricultural and municipal waste into fuels, polymers, and fertilizers, closing loops across entire industrial sectors. This global shift makes industry regenerative rather than extractive, decoupling prosperity from ecological destruction. Vegan technologies offer the blueprint for cities and industries that are not merely sustainable but actively regenerative. By redesigning food systems around plants, fungi, and microbes, replacing animal-based and fossil-based materials with biocomposites, embedding circular waste-to-value systems, and integrating renewable-powered water and energy solutions, humanity can create cities that function like ecosystems. Urban environments enriched with green and blue infrastructure can sequester carbon, restore biodiversity, and provide resilient livelihoods. When supported by digital optimization and bold governance, vegan technologies allow industries to thrive without exploitation or pollution. Together, these innovations transform cities from centers of ecological damage into engines of planetary regeneration. How can we build a regenerative vegan city of the future? How to build a regenerative vegan city of the future. Here is a practical, comprehensive blueprint for designing, building, and operating a regenerative vegan city. I explain guiding principles, the physical and social systems you must design, food, energy, water, materials, waste, transport, buildings, industry, governance and finance, and implementation timeline, metrics for success, likely risks, and concrete next steps. Every section is written in complete sentences. Vision and guiding principles. A regenerative vegan city prioritizes plant and microbe-based production, eliminates reliance on industrial animal agriculture, restores ecosystems, and circulates materials and nutrients so that natural systems are enhanced rather than depleted. The city designs infrastructure so that it produces more ecosystem services than it consumes, including carbon sequestration, clean water, biodiversity habitat, and fertile soils. Equity, local self-reliance, resilience to shocks, and cultural inclusion are core values that guide every decision. Urban form and land use design. The city uses compact, transit-oriented development to minimize land take while reserving extensive peripheries and corridors for rewilding, agroforestry, and carbon-rich habitat. Green corridors and connected urban forests weave through neighborhoods to preserve biodiversity and provide cooling. Rooftops, facades, and vacant lots are treated as productive land for food or biomass production. Peri-urban rings host larger agroforestry farms, algal ponds, and biorefineries that serve the city while returning nutrients to the landscape. Food systems, production, processing, and distribution. The city combines distributed and regional vegan food production to maximize resilience and minimize resource use. Vertical farms and controlled environment agriculture in dense neighborhoods supply fresh greens, herbs, and specialty crops year-round. Community orchards, food forests, and agroforestry on public land supply fruit, nuts, and biomass while enhancing habitat. Precision fermentation hubs located near demand produce proteins, fats, and specialty ingredients using low-carbon electricity. Algae and seaweed cultivation in coastal or inland closed-loop ponds provide oils, pigments, and fertilizer inputs. Local processing facilities convert plant residues into flours, fiber materials, mycelium substrates, and fermented products so that most food value capture remains local. Distribution networks prioritize short supply chains, cooperative markets, and municipal procurement for schools and hospitals. Energy and decarbonization. The city runs on an integrated, mostly renewable energy system composed of rooftop and utility-scale solar, distributed wind, geothermal where available, and bioenergy from sustainably sourced plant residues and anaerobic digestion of plant waste. Energy storage combines batteries, thermal stores, and chemical storage produced in biorefineries. All high-energy processes, fermentation, desalination, vertical farms, are designed for energy efficiency and located to take advantage of waste heat and local renewables. District heating and cooling platforms reuse process heat from industrial hubs to serve adjacent residential and farming facilities. Water systems and hydrology. Water systems prioritize capture, reuse, and ecosystem-based treatment. The city implements rainwater capture on every rooftop, permeable pavements, and restored wetlands for stormwater retention. Constructed wetlands and plant-based biofiltration treat graywater and blackwater, returning treated water to irrigation and aquifer recharge. Solar-powered desalination supplies coastal needs while brine and byproducts are handled with environmental safeguards. Water-smart agricultural systems, drip irrigation, aeroponics, and fog harvesting minimize freshwater consumption. Materials, buildings, and circular industry. Buildings and industry use low-embodied carbon, plant and fungal-based materials. Hempcrete, bamboo, cross-laminated timber from sustainably managed sources, mycelium insulation, and straw board panels are the default choices for new construction. A municipal materials hub collects urban plant waste, textile scraps, and agricultural residues and routes them to mycelium factories, biorefineries, and fiber processors. The city favors modular buildings designed for disassembly so materials can return to the biological cycle at end of life. Procurement standards require compostability or recyclability for all packaging and products bought by the city. Waste-to-value and nutrient cycling. All organic waste streams are treated as valuable feedstocks rather than garbage. Citywide source separation ensures that plant-based food waste goes to anaerobic digesters for biogas and digestate, or to high-quality composting systems for soils. Digestate and compost are used by urban farms and peri-urban agroforestry. Industrial residues are processed in a regional biorefinery to produce bioplastics, platform chemicals, and fertilizers. A nutrient tracking digital platform records flows of carbon, nitrogen, and phosphorus so that shortages and surpluses can be managed in real time. Transportation and logistics. Transportation is designed to be low carbon, space efficient, and compatible with vegan supply chains. The city prioritizes walking, cycling, and high-quality public transit. Last-mile delivery for food and materials uses electric cargo bikes and small electric vans routed by AI to minimize mileage. Freight hubs are sited nearby refineries and fermentation centers to reduce transport of heavy biomass. Active logistics networks enable efficient redistribution of surplus plant food to community kitchens and composting facilities. Biodiversity and ecosystem restoration. The city invests in large-scale rewilding of peripheral lands and restoration of riparian corridors, wetlands, and coastal mangroves where applicable. Urban green spaces are planted with native species to support pollinators and birds. Rooftop and vertical gardens use diverse polycultures rather than monocultures to enhance habitat value. Ecological corridors connect urban and peri-urban habitats to enable species movement and genetic exchange, which supports resilience and long-term ecosystem recovery. Governance, policy, and finance. Local governments set binding targets for zero animal-derived procurement in municipal services within a defined time frame and prioritize plant-based alternatives in public contracts. Zoning codes and building regulations are revised to permit and incentivize rooftop farms, fermentation hubs, and green infrastructure. A blend of public funding, green bonds, impact investment, and public-private partnerships finances large infrastructure projects such as biorefineries and district energy. Payments for ecosystem services and municipal carbon credits reward landowners who commit land to rewilding and agroforestry. Community land trusts and cooperative ownership models keep benefits local and equitable. Social systems, workforce, and culture. The city invests in workforce retraining programs that transition workers from extractive industries to regenerative sectors such as mycelium fabrication, vertical farming operations, and biorefinery maintenance. Food education programs in schools teach culinary skills around plant and microbe-based foods. Small business incubation supports artisan biomaterials, seaweed processing, and plant-based food startups. Democratic participatory planning includes neighborhood councils, indigenous stewardship boards, and labor representatives so that cultural values and local knowledge shape the transition. Digital infrastructure and measurement. A transparent data platform monitors greenhouse gases, soil organic carbon, biodiversity indices, water use, and nutrient flows in near real time. Open data and clear reporting build public trust and allow adaptive management. Digital platforms match surplus food with community needs, connect farmers to processors, and coordinate maintenance of green infrastructure. Standards and interoperable data formats ensure accountability and facilitate carbon credit verification and payments for ecosystem services. Implementation timeline: short, medium, and long-term. Short-term, 0 to 3 years. Implement municipal procurement rules favoring plant-based foods and bio-based materials. Start rooftop and neighborhood pilot vertical farms, citywide composting and anaerobic digestion programs, and a seed fermentation hub. Pass zoning changes to allow urban food production and small-scale biomanufacturing. Medium term, 3 to 10 years. Scale precision fermentation and mycelium factories. Build regional biorefineries and district energy networks that reuse waste heat. Convert marginal pasture and peri-urban farmland to agroforestry and perennial systems. Expand green corridors and constructed wetlands. Long-term, 10 to 30 years. Achieve near-complete circularity for organic streams, large-scale rewilding of freed agricultural land, and full integration of food, energy, water, and material flows so that the city becomes net positive in carbon sequestration and biodiversity outcomes. Institutionalized training pipelines and transition finance mechanisms for a resilient regenerative economy. Metrics of success. The city tracks a concise set of metrics including net greenhouse gas emissions, Scope 1 and 3, area of land returned to native habitat, soil organic carbon increases per hectare, percentage of food sourced from local plant and microbe-based systems, volume of organic waste diverted to composting or digestion, biodiversity indices for native species, freshwater use per capita, and the share of municipal procurement that is vegan compliant. Social metrics include jobs created in regenerative sectors, income stability during transition, and equitable access to green spaces and fresh food. Risks and mitigation. A key risk is substituting monoculture plant production for animal agriculture, which could perpetuate biodiversity loss. The city mitigates this by requiring polyculture designs, agroforestry, and strict land use protections. Energy-intensive systems such as vertical farms and fermentation plants pose climate risks if the grid is not clean. This is mitigated by prioritizing renewable energy and waste heat integration. Social displacement is a risk. It is mitigated by inclusive planning, cooperative ownership models, and dedicated transition funds for affected communities. Example technologies and actors to deploy core technologies include modular vertical farm units, precision fermentation bioreactors sized for municipal hubs, insulated algal phenobioreactors for rooftop use, mycelium manufacturing kilns, anaerobic digesters tailored for plant waste, modular biorefinery components for producing bioplastics and chemical feedstocks, and software platforms for nutrient tracking and logistics. Effective actors include municipal governments, community land trusts, regional utilities, research universities, local cooperatives, impact investors, and civil society organizations that ensure equitable governance. Concrete next steps. First 12 months, adopt a municipal vegan procurement policy for schools, hospitals, and government facilities with clear timelines. Launch 3 pilot projects, a rooftop vertical farm, a neighborhood composting and anaerobic digestion center, and a small precision fermentation pilot. Revise zoning and building codes to enable rooftop and facade farming as well as neighborhood biomanufacturing. Create a community transition fund for workers and farmers to support retraining and pilot agroforestry conversions. Set up an open data dashboard to begin tracking baseline metrics for emissions, land use, biodiversity, and food sourcing. Building a regenerative vegan city is a systems challenge, but it is technically and socially feasible. By combining distributed plant production, microbial manufacturing, plant and fungal-based materials, circular waste and nutrient systems, renewable energy, and inclusive governance, a city can become net positive for biodiversity and carbon while providing equitable livelihoods and healthy food for its residents. The transition requires political will, financing, community buy-in, and careful ecological design, but the result is a resilient, just, and flourishing urban ecosystem. What are the most sustainable and regenerative systems to build vegan cities around the world? Most sustainable and regenerative systems to build vegan cities around the world. Here is a list of the highest leverage systems that a city should center its planning on when designing a truly sustainable, regenerative, and vegan. First, urban future. Each item is explained in complete sentences, includes why it matters, a note on trade-offs or operational considerations, and one practical action a city can take to implement it at scale. Locally distributed plant and microbial food systems. Locally distributed food systems combine vertical farms, rooftop and community gardens, peri-urban agroforestry, precision fermentation hubs, and algal cultivation so that most calories and high-value ingredients are produced near demand. These systems reduce food miles, lower dependence on animal agriculture, and free rural land for rewilding. The main trade-off is that some high-tech units require reliable energy and skilled operators, so hybrid approaches that mix low-tech community gardens with commercial controlled environment farms create resilience. A practical first step is to map vacant rooftops and municipal land for pilot vertical farms and community orchards, tied to a local fermentation prototype. Circular organic waste and nutrient management. A regenerative vegan city treats all plant and food waste as feedstock rather than garbage by using source separation, municipal composting, high-quality anaerobic digestion, and urban biorefineries that turn residues into fertilizers, soil amendments, bioplastics, and platform chemicals. This closes nutrient cycles, rebuilds soil, and reduces methane emissions from landfills. Operational challenges include maintaining clean source streams and building stable demand for outputs, which can be solved by municipal procurement and municipal garden networks. A practical action is to require source-separated organic collection and fund a regional composting facility with guaranteed offtake for urban farms. Low embodied carbon, biomaterial-based construction and manufacturing. Cities should substitute concrete, steel, and animal-derived materials with concrete, cross-laminated timber from sustainably managed sources, mycelium composites, straw panels, and recycled plant fiber composites so that embodied carbon is minimized and materials return safely to the biosphere at end of life. The implementation challenges certification and building code updates, so pilot public buildings using these materials help prove performance and update standards. A practical action is to adopt a municipal procurement policy that gives preference to verified low-embodied carbon bio-based materials for public projects. Integrated renewable energy with waste heat reuse. Renewable electricity, primarily rooftop and utility solar, distributed wind, geothermal where appropriate, and community microgrids, must power urban farming, desalination, fermentation, and processing facilities so that these systems are truly low carbon. Waste heat recovery from industrial hubs should be looped into district heating and greenhouse systems to improve overall efficiency. The main consideration is balancing variable renewables with storage needs. Combining batteries, thermal stores, and chemical storage in biorefineries creates flexibility. A practical step is to plan renewable generation near high-demand clusters, vertical farms, fermentation hubs, and design those facilities to use captured process heat. Water circularity and nature-based treatment. Cities should employ water capture and reuse strategies, rainwater harvesting, greywater reuse, decentralized treatment, constructed wetlands, and solar-driven desalination for coastal cities, so that potable supplies are conserved and ecosystems are protected. Nature-based treatment systems both clean water and provide habitat, but they require land and ongoing maintenance, which can be integrated into parks and multifunctional public spaces. A practical action is to retrofit municipal buildings with rainwater harvesting and install constructed wetlands for neighborhood wastewater treatment linked to irrigation for urban farms. Urban biodiversity networks and peri-urban rewilding. A vegan regenerative city stitches together urban green corridors, food forests, pollinator habitats, riparian restoration, and large peri-urban rewilding and agroforestry belts so that biodiversity recovers and ecosystem services such as pollination, flood mitigation, and microclimate regulation are provided locally. The trade-off is land allocation versus densification pressures. This is resolved by compact urban design paired with legally protected peri-urban conservation areas. A practical immediate step is to create legally binding biodiversity corridors and convert a percentage of public green space to native polycultures and food forests. Decentralized biomanufacturing and material hubs. Local hubs that produce mycelium products, plant fiber textiles, algae-derived chemicals, and precision-fermented ingredients keep value local and reduce embodied emissions from long supply chains. These hubs also provide jobs and enable rapid circular loops. Challenges include scaling quality control and regulatory approval, so cities can incubate pilot hubs with university partnerships and fast-track micro-production permits. A practical action is to create an industrial cluster zone with shared utilities for small biomanufacturers and an on-site lab support facility. Smart logistics, low-impact transport, and last-mile electrification. A city that prioritizes walking, cycling, public transit, and electric last-mile logistics reduces emissions and space wasted by cars. Efficient logistics tailored to perishable plant-based foods, using electric cargo bikes and urban consolidation centers, reduces spoilage and carbon footprints. The principal trade-off is upfront infrastructure and behavior change, which are addressed through incentives, redesign of streetscapes, and congestion pricing. A practical step is to create low-traffic neighborhoods, build protected bike lanes, and subsidize electric cargo vehicle fleets for local food distribution. Digital platforms for material, nutrient, and data circulations. Open data platforms for tracking organic flows, soil carbon, biodiversity, water use, and supply chain provenance enable adaptive management and credible verification of regenerative outcomes. Digital nudges in marketplaces match surplus food to social programs and redirect residues to biorefineries. Data governance and privacy are important considerations, so civic data trusts and transparent governance structures should be used. A practical action is to pilot a nutrient tracking dashboard that shows compostable volumes, soil returns, and supply chain footprints for municipal stakeholders. Policy, finance, and governance mechanisms that enable transitions. Regenerative vegan cities require policy levers such as vegan procurement mandates, zoning that allows rooftop farms and microbiofactories, subsidies for regenerative farming conversion, payments for ecosystem services, and public investment in circular infrastructure. Financial instruments like green bonds, transition funds for workers, and community ownership models ensure equitable benefits. Political feasibility is the main constraint, so phased targets, pilot successes, and clear economic case studies accelerate uptake. A practical near-term policy is to require that a share of municipal food procurement be plant-based and locally produced within 5 years. Workforce development and community participation. A successful transition depends on retraining workers, creating pathways into mycelium fabrication, fermentation, vertical farming, biorefinery operation, and ecosystem restoration, and designing projects with communities and indigenous stewards. Social equity must be built into planning to avoid displacement. A practical first action is to fund accredited training programs linked to municipal procurement pipelines so graduates have guaranteed market access. Monitoring, metrics, and verification systems. A vegan regenerative city should track a concise set of indicators: net GHG balance, including methane and nitrous oxide, hectares restored or returned to native vegetation, soil organic carbon change, local food production share, organic waste diversion rates, biodiversity indices, freshwater use per capita, and social equity metrics such as local green jobs created. Accurate measurement enables continuous improvement, but measurement can be costly. Cities can begin with sentinel sites and scale monitoring as capacity grows. A practical step is to publish an annual regenerative city scorecard using third-party verification. Typical risks and straightforward mitigations. A common risk is replacing animal systems with new monocultures, which would harm biodiversity. The mitigation is to mandate polycultures, perennial systems, and agroforestry in all agricultural incentive programs. Another risk is high energy use for controlled environment agriculture and fermentation, which is mitigated by pairing these systems with renewables and waste heat capture. A third risk is social displacement from rapid redevelopment, which is mitigated by community land trusts, inclusionary zoning, and job guarantees. Each mitigation is best implemented through integrated policy design rather than single project fixes. Start a portfolio of high-impact pilot projects, first 1 to 3 years, a neighborhood rooftop-to-basement pilot combining a vertical farm, an algal phenolbioreactor installation, and a community fermentation kitchen that supplies schools. A municipal organic waste program that includes curbside separation, a medium-scale anaerobic digester, and a compost distribution network to urban farms. A public building retrofit using hempcrete and mycelium insulation with an adjacent demonstration mycelium manufacturing hub. A peri-urban agroforestry conversion program that pays farmers to transition marginal pasture into food forests and carbon sequestering perennials. These pilots prove technology combinations, build workforce capacity, and create visible community benefits. How to scale from pilots to citywide transformation. Cities scale by codifying successful pilots into policy, securing financing through public bonds and private-public partnerships, and building regional networks that replicate proven hubs. Metrics from pilots should feed into procurement rules and zoning updates, and successful small enterprises should be supported to expand regionally. Regional collaboration, sharing renewable energy, logistics, and processing capacity, amplifies benefits and prevents competitive fragmentation. The most sustainable and regenerative vegan cities are ones that treat plant and microbial systems as the primary production engines, close nutrient and material loops, center renewable energy and water circularity, restore urban and peri-urban ecosystems, and align policy, finance, and social systems to ensure equity and resilience. By sequencing pilots in food, waste, materials, and energy and then embedding successful models into regulation and procurement, cities worldwide can transition to regenerative, vegan-centered economies that heal the biosphere while providing prosperous, just urban lives. What are the best vegan systems that can turn the world extremely green and self-sustaining? Here is a comprehensive, clearly written explanation of the best vegan systems, meaning plant, fungal, algal, and microbe-centered systems that, if scaled and integrated worldwide, could make the planet vastly greener, more self-sustaining, and ecologically resilient. Each system is explained in complete sentences with why it matters, how it works, key trade-offs or risks, and concrete actions to scale it. Regenerative plant agriculture and perennial polycultures. Regenerative plant agriculture replaces extractive, high-input monocultures and animal-heavy systems with diversified cropping systems that rebuild soil health and store carbon. Perennial polycultures, agroforestry, alley cropping, and food forests keep living roots in the ground year-round, which increases soil organic matter, stabilizes microclimates, reduces erosion, and supports biodiversity. The primary trade-offs are the time and transitional costs required to establish perennial systems and the need for new market channels for diversified yields. To scale, governments and funders should create multi-year transition payments for farmers, invest in breeding perennial staples, and build supply chains and processing for diverse crops. Large-scale rewilding and natural regeneration of freed agricultural land, when land freed from livestock and feed production is legally protected and actively rewilded. Native ecosystems regrow and sequester large amounts of carbon while restoring biodiversity and hydrological cycles. Natural regeneration, assisted reforestation, and ecological corridor creation revive ecosystem functions most cost-effectively in many regions. The main risk is that rewilding can conflict with local livelihoods if transitions are not inclusive. Equitable land stewardship models and payments for ecosystem services schemes help mitigate that risk. Immediate actions include mapping high-priority lands for rewilding and directing subsidy reform and carbon finance to support landowner transitions. Precision fermentation and microbial protein. Single-cell protein precision fermentation produces proteins, fats, enzymes, and specialty biomolecules using microbes and controlled bioreactors, while single-cell protein, from yeast, bacteria, fungi, or algae, provides high-quality food and feed with tiny land footprints. These technologies eliminate most demand for animal production while dramatically reducing land, water, and methane emissions. The trade-offs include energy use and the need for low-carbon electricity. Therefore, pairing fermentation with renewable energy and waste heat reuse is essential. Scaling requires public support for pilot plants, regulatory frameworks for novel foods, and investment in distributed fermentation hubs near markets. Mycelium and fungi-based manufacturing. Mycelium can be grown on agricultural residues to create leather substitutes, insulation, packaging, and construction materials that biodegrade safely at end of life. Fungal biomanufacturing also produces flavors, enzymes, and specialty biomaterials. These systems turn waste into high-value products and reduce reliance on fossil plastics and animal leather. Challenges include industrial standardization and scaling consistent material properties. These are addressed with R&D, standard testing frameworks, and industrial pilot facilities. Policy support for circular procurement and industry incentives speeds market development. Algae and seaweed biorefineries. Blue-green economies. Cultivating microalgae and macroalgae produces food, feed, fertilizers, biofuels, bioplastics, and specialty chemicals while absorbing CO2 and improving local water quality. Seaweed farms also restore coastal ecosystems, buffer shorelines, and create livelihoods that do not depend on extractive animal fisheries. The primary logistical challenge is processing wet biomass cost-effectively. Centralized and distributed drying and fractionation facilities solve this while enabling diverse product pathways. Scaling requires investment in coastal permitting frameworks, farmer training, and downstream processing infrastructure. Circular organic waste systems and urban nutrient loop. Cities and industries generate massive amounts of plant-based organic waste that can be transformed into compost, digestate, biochar, single-cell protein feedstock, or inputs for fermentation and mycelium production. Closing nutrient loops prevents pollution, rebuilds soils, and retains nutrients on the landscape. The technical and governance challenge is reliable source separation and markets for outputs. Municipalities should mandate organics diversion, finance compost at infrastructure, and use public procurement to create demand for compost and biochar. Water-smart vegan food systems, hydroaeroponics, halophytes, fog harvesting, water-efficient systems such as drip irrigation, hydroponics, aeroponics, salt-tolerant halophyte farming, and fog dew harvesting enable abundant plant production with minimal fresh water. These systems are essential in arid regions and for reducing pressure on freshwater ecosystems. Energy and technical needs can be limiting. Pairing systems with renewables and local maintenance training overcomes these barriers. Pilot demonstration projects and subsidies for water-saving infrastructure accelerate adoption. Biochar, soil microbiome restoration, and microbial biofertilizers. Biochar and microbiome-focused amendments stabilize soil carbon, improve water retention, and boost nutrient cycling so that plant systems become productive and resilient without relying on animal manures. Microbial inoculants, nitrogen-fixing bacteria, mycorrhizae, increase nutrient use efficiency and reduce fertilizer needs. The risks include variable outcomes across soil types. Therefore, regional field trials and farmer-led research networks are essential to identify best practices. Scaling requires investment in decentralized production units and extension services. Decentralized renewable energy coupled to biological production. Renewable electricity, solar, wind, geothermal, and distributed microgrids must power fermentation, desalination, vertical farming, and biorefineries to ensure vegan systems are low carbon. Waste heat recovery and thermal storage should be standard design features so biological processes use energy efficiently. Policy mechanisms such as feed-in tariffs, community ownership models, and green bonds can finance the required renewable capacity. Low embodied carbon, bio-based construction and circular materials economy replacing concrete, steel, and animal-derived materials with concrete, bamboo, timber from sustainable sources, straw board, and mycelium panels reduces embodied emissions and locks carbon in long-lived structures. Designing for disassembly ensures materials re-enter biological cycles at end of life. Standards, building code updates, and public demonstration projects to risk adoption and create markets for bio-based construction. Scaled urban-rural integration and peri-urban agroecology, integrating dense urban centers with productive peri-urban agroforestry belts and regional biorefineries creates resilient, short supply chains and retains nutrient cycles within regions. This spatial integration reduces transport emissions and enables cities to absorb and return nutrients via compost and digestate. Land use planning, regional food councils, and incentives for peri-urban regenerative practices enable this integration. Biodiverse food systems and seed sovereignty, maintaining seed diversity and supporting locally adapted, biodiversity-friendly crop varieties reduces pest risk, improves nutrition, and supports resilient agroecosystems. Seed sovereignty programs, community seed banks, and decentralized seed breeding for perennial and polyculture systems are essential for long-term sustainability. Policy support and funding for community breeding projects help scale resilient seeds worldwide. Digital platforms for optimization, traceability, and matching supply-demand. Open, interoperable digital systems track nutrient flows, energy use, soil carbon, and biodiversity outcomes while matching supply of biomass residues to local processors. Traceability platforms encourage regenerative practices by providing premium market access. Data governance frameworks and equitable access to tools are required so smallholders and communities can participate. Policy, finance, and social instruments to enable rapid transition. Systemic change requires redirecting subsidies from animal feed and fossil inputs to regenerative plant and microbial systems, paying land stewards for ecosystem services, and financing worker retraining. Instruments such as transition funds, green bonds earmarked for bio-based infrastructure, green public procurement, and verified carbon and biodiversity credits speed adoption while protecting livelihoods. Education, cultural shift, and local empowerment. A global vegan regenerative transition requires cultural and dietary shifts supported by education, culinary innovation, and local food traditions that emphasize plant and microbe-based diets. Vocational training programs, university curricula in biomanufacturing and agroecology, and community co-design processes ensure social buy-in and create the workforce needed to operate these systems. Integrated implementation pathway, how these systems work together. Phase 1, 0 to 5 years, start pilot hubs, regional fermentation plants, mycelium factories, urban composting and anaerobic digestion sites, and peri-urban agroforestry demos, paired with renewable microgrids. Establish seed banks and farmer training programs. Reform subsidies to fund transition contracts. Phase 2, 5 to 15 years, build networks of biorefineries, algal processing centers, and distributed fermentation hubs. Scale perennial polycultures and rewilding on lands freed from animal agriculture. Update building codes and procure bio-based materials for public infrastructure. Phase 3, 15 to 30 years, achieve near closed-loop nutrient cycling at regional scales, mainstreaming plant and microbe-based foods and materials. Rewild a significant fraction of formerly grazed and feed croplands. Institutionalize payments for ecosystem services and embed regenerative standards in global trade. Metrics to monitor success. Success should be measured by a concise suite of indicators: net greenhouse gas balance, including methane and nitrous oxide, hectares of native habitat restored, soil organic carbon stock changes, fresh water use per unit food produced, percent of calories protein supplied by plant and microbial sources, volume of organic waste diverted to productive use, biodiversity indices, and socioeconomic indicators such as jobs created in regenerative sectors and income stability for transitioning farmers. Major risks and how to mitigate them. A major risk is simply replacing animal agriculture with large-scale monoculture crops. This would repeat past harms. The mitigation is explicit policy and design requirements for polycultures, perennial systems, agroforestry, and landscape-level biodiversity planning. Another risk is energy intensity of some biomanufacturing. The mitigation is strict coupling to renewables and waste heat recovery. Social displacement is a risk that should be handled through just transition funds, community ownership models, and participatory planning. The highest leverage stack. If one had to prioritize 3 systems for immediate global scaling to make the world extremely green and self-sustaining, they would be regenerative perennial polycultures plus agroforestry, to rebuild soils and sequester carbon at landscape scale; precision fermentation plus single-cell protein plus algal biorefineries, to replace animal-derived calories and industrial inputs with tiny land and water footprints; circular organic waste systems plus mycelium manufacturing, to close nutrient loops and convert waste into valuable biodegradable materials. These three, implemented together and powered by distributed renewable energy, create a resilient, circular, and biodiverse global economy that is plant and microbe-centered rather than animal-dependent.